Space-time has never been a fundamental aspect of reality. I am not merely suggesting it doesn't exist currently or that it originated with the Big Bang. I am stating that it has never been real, not for a single instant, not in any region of the cosmos. Space-time is not a fundamental entity. It has never been one. It is a mirage, a convenient narrative, a higher-level description that arises from something entirely more basic. This likely sounds absurd, I understand. At this very moment, you are situated somewhere, occupying a location, feeling the passage of moments. How could I possibly assert that space-time has never been real? However, after many years of research into quantum mechanics, black holes, string theory, and the holographic principle, I have reached a firm conclusion. Space-time is not a primary ingredient of the universe. It is an emergent phenomenon, and anything that is emergent did not truly exist in a foundational sense. Allow me to clarify this perspective and present the substantial evidence that supports it. First, I must define what I mean by never existed. I am not claiming space-time is a pure fantasy with no connection to the real world. I am arguing it is analogous to temperature or to ocean waves. These are genuine at the everyday scale, real as collective phenomena, but they are not elementary. They arise from more fundamental components. Temperature represents the average kinetic energy of countless molecules. It is real in that you can measure it, sense it, and use it in equations. But a single molecule does not possess temperature. Temperature only becomes meaningful when you have a vast collection of molecules and you perform a coarse graining procedure, averaging over the microscopic details. Before there were many molecules, before there existed a macroscopic system to average over, temperature did not exist. This isn't because temperature suddenly came into being later. It's because temperature is an emergent property that only has meaning at a particular scale. Space-time is similar. It is an emergent property of quantum information, quantum entanglement, and degrees of freedom we do not yet fully comprehend. Without the appropriate organization of quantum information, there is no space-time. And by before, I do not mean a moment in time prior, because time itself is part of what emerges. Space-time never existed as a fundamental entity. It exists solely as an emergent description. And emergent phenomena are not real in the foundational sense. My journey to this belief began with black holes and the information paradox. When Stephen Hawking demonstrated that black holes emit radiation and eventually evaporate, he concluded that information is obliterated. Anything that falls into a black hole is permanently lost when the hole evaporates. But this violates quantum mechanics, which insists information must be preserved. So either quantum mechanics is incorrect, or our understanding of black holes is flawed. I spent years debating this with Hawking. The resolution I arrived at is that the interior of a black hole is not a real independent region of space. All information about the black hole and everything that ever fell in is encoded on its two-dimensional event horizon. The interior is a holographic projection from the horizon's data. But if a black hole's interior is not fundamentally real, if it is merely a derived description of information on the horizon, then what about space in general? If three-dimensional space can be illusory for black holes, perhaps it is illusory everywhere. This led to the holographic principle, which Gerard 't Hooft and I developed. The principle proposes that all information contained within a volume of space is encoded on the boundary of that volume. The interior is redundant, derivable from boundary data. For a black hole, this is concrete. Its entropy is proportional to the horizon's area, not its volume. The information resides on the surface, not within. The three-dimensional interior emerges from two-dimensional information. If this applies to black holes, it likely applies universally. Our entire three-dimensional universe might be a holographic projection from information on a two-dimensional surface. The third spatial dimension may have never existed as a fundamental entity. Space, at least one dimension of it, is emergent. It never existed fundamentally. Then came the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. This was the rigorous proof we needed. Maldacena showed that a gravitational theory within a space of 3 spatial dimensions is exactly equivalent to a quantum field theory living on the 2-dimensional boundary of that space. In the boundary theory, there is no bulk space. There are only quantum fields existing on a 2-dimensional surface. No third dimension, no interior, just the boundary. Yet, from this boundary theory, you can derive the existence of the bulk space. The interior emerges from specific entanglement patterns within the boundary quantum fields. Space itself emerges from quantum information. This proves the concept. Space can emerge from non-spatial quantum information, and if it emerges, it never existed fundamentally. The boundary theory is the underlying reality. The bulk space is the illusion. In AD-S-CFT, space literally never existed at the fundamental level. The foundational description has one fewer spatial dimension. Space in the bulk is an emergent derived concept. Our universe is not exactly anti-de Sitter space, so we lack a complete holographic description for it yet. But the principle should apply. The mathematics is too elegant, too powerful, and too explanatory to be mere coincidence. If space can emerge in AD-CFT, it likely emerges in our universe too. And if it emerges, it never existed fundamentally. Another compelling reason space-time never existed is this: quantum entanglement creates geometry. This is one of the most profound insights from AD-S-CFT and subsequent work. The distance between 2 points in the emergent bulk space is related to the degree of entanglement between corresponding regions in the boundary theory. Strongly entangled regions correspond to nearby points in space. Weakly entangled regions correspond to distant points. This is made precise by the Ryu-Takayanagi formula. The entanglement entropy of a region in the boundary theory equals the area of a minimal surface in the bulk that separates that region from its complement. Consider what this implies. Space, geometry, distance, all these emerge from patterns of entanglement. At the boundary level, there is no space. There is only quantum information, qubits entangled with each other in complex ways. When you have the correct entanglement structure, when quantum information is organized in specific patterns, the appearance of space emerges. You can describe the same physics using the language of geometry, of points separated by distances, but the space is not fundamental. It never existed prior to the entanglement pattern, and the entanglement pattern itself is not spatial. It is merely relationships between quantum degrees of freedom. Space emerges from entanglement. Before entanglement organized itself appropriately, there was no space. Space never existed as a thing in itself. It has always been a description of entanglement patterns. Now, let's consider time. If space is emergent, what about time? Here, the situation is even more radical. Time might not exist, even as an emergent phenomenon in the usual sense. At the most fundamental level, in the deepest quantum description, there may be no time at all. The Wheeler-DeWitt equation, which attempts to describe quantum cosmology, contains no time variable. The wave function of the universe does not evolve in time. It simply is. Time emerges when you divide the universe into subsystems. When you use part of the universe as a clock to track changes in the rest, different divisions yield different notions of time. But at the foundational level, there is no time. This is profoundly counterintuitive. Our entire experience is temporal. We age, we remember the past, we anticipate the future. Yet that experience might be an illusion, an emergent property of how we, as subsystems of the universe, correlate our internal states with external events. Time never existed as a fundamental flow. It emerges from correlations within a timeless quantum state. There is another aspect. The arrow of time, the direction from past to future, is thermodynamic. It is defined by increasing entropy. Low entropy is the past, high entropy is the future. But entropy is a coarse-grained concept. It concerns our ignorance of microscopic details. At the fundamental microscopic level, dynamics are time-symmetric. There is no intrinsic arrow. The arrow of time emerges when you coarse-grain, when you average over unobserved degrees of freedom. It is not a fundamental feature of time itself. So, time never existed as a fundamental directed flow. The flow, the arrow, the passage of time. All of it emerges from time-symmetric fundamental dynamics, combined with coarse graining. Space-time never existed because space is emergent from entanglement, and time is emergent from correlations and coarse graining. Neither is fundamental. Evidence from string theory further supports this. In string theory, the fundamental objects are one-dimensional strings vibrating in a higher dimensional space. Different vibration modes correspond to different particles. However, the space the strings inhabit is not necessarily physical space-time. It is a mathematical configuration space. The physical space-time we experience emerges from the dynamics of strings. In some formulations, like matrix theory, there is no background space-time whatsoever. Space-time emerges from the interactions of matrix degrees of freedom. Before you activate the interactions, there is no space, no time, only matrices. This is radical. It means space-time is not the stage upon which physics happens. Space-time is part of what emerges from the physics. The fundamental description is non-spatial and non-temporal. Space-time never existed in string theory as a fundamental background. It emerges from stringy dynamics. What then exists if space-time does not? What is the fundamental reality? The answer, I believe, is quantum information. At the most basic level, reality consists of quantum degrees of freedom, qubits, if you will, existing in a Hilbert space, not in a physical space. These qubits interact, become entangled, and form complex patterns of correlation. From these patterns, when you coarse grain and examine collective behavior, space-time emerges. The qubits do not exist in space. They do not evolve in time in the fundamental description. They simply exist in a timeless quantum state. Space-time emerges when you describe this state in particular ways. What existed before space-time? Not before in a temporal sense, because time is part of what emerges, but more fundamentally, quantum information existed. Entanglement existed. The laws of quantum mechanics existed. Space-time never existed because quantum information is more fundamental, and space-time is merely a way of organizing and describing that information. Consider an analogy. Imagine a computer running a simulation of a three-dimensional world. On the screen, you see a 3D space with objects moving through time. But what is truly happening? The computer is processing bits, ones and zeros, according to the rules of the simulation. The 3D space on the screen is not fundamental. It is a display, a user interface generated by information processing. The fundamental reality is the bits and the algorithm. The 3D space is emergent, a way of organizing the output that is intuitive for human observers. Our universe might be similar. The fundamental reality is quantum information, qubits and entanglement patterns. Space-time is the display, the user interface, the way this information manifests to observers embedded within it. Space-time never existed as the fundamental reality. It has always been the interface generated by the processing of quantum information. Now consider the Big Bang. If space-time is emergent, what does it mean to say space-time began at the Big Bang? In the traditional picture, space-time literally came into existence 13.8 billion years ago. Before that, there was nothing, not even space or time. The Big Bang is the beginning of space-time itself. But if space-time is emergent, this picture shifts. The fundamental quantum state might be timeless, existing independently of the space-time that emerges from it. The Big Bang is not the beginning of existence. It is the beginning of the emergent space-time description. It is the point where space-time emerges from the timeless quantum state, where the approximation of classical geometry becomes valid. Before the Big Bang, in the fundamental description, there was quantum information in some configuration. There was no space, no time, but there was quantum structure. The Big Bang is an emergent phenomenon, the birth of space-time as a useful description, not the birth of reality itself. Space-time never existed before the Big Bang because space-time itself is emergent. What is fundamental is the timeless quantum state. Another implication involves the Planck scale. At distances around 10 or 35 meters and energies around 1019 GeV, quantum gravity effects dominate. This is the Planck scale. At this scale, our smooth notion of space-time breaks down. Space becomes foamy, fluctuating, and uncertain. Time becomes ill-defined. The classical geometry of general relativity fails. Why does space-time break down at the Planck scale? Because that is the scale where the emergent description fails, where you are probing so close to the fundamental degrees of freedom that the approximation of smooth space-time ceases to work. It is like zooming in on a digital photograph. From a distance, it looks smooth and continuous, but zoom in enough and you see discrete pixels. The smoothness was an illusion of coarse graining. Space-time is smooth at large scales because you are averaging over many fundamental degrees of freedom. At the Planck scale, you encounter the individual degrees of freedom, and the smoothness vanishes. Space-time never existed as a smooth continuum. It has always been a coarse-grained description of discrete quantum information. What does this mean for general relativity? Einstein's theory is profoundly beautiful. Space-time is dynamic, curved by matter and energy. Gravity is geometry. However, general relativity is a classical theory that assumes smooth space-time. If space-time is emergent, then general relativity is an emergent theory, valid in the limit where quantum effects are negligible and coarse graining applies. Einstein's equations are not fundamental laws. They are effective equations describing the dynamics of emergent space-time geometry. The fundamental laws govern quantum information, and Einstein's equations emerge from them. This does not diminish Einstein's achievement. It clarifies its place in the hierarchy of theories. General relativity is correct as an emergent description, spectacularly successful in its domain, but it is not fundamental. Space-time never existed at the fundamental level, so a theory describing its geometry, however elegant, cannot be fundamental. Consider the ER-SAR-EPR idea that Maldacena and I proposed. ER stands for Einstein-Rosen bridges, wormholes connecting distant points in space. EPR stands for Einstein-Podolsky-Rosen entangled quantum states. Our proposal is that they are the same phenomenon. When two quantum systems are entangled, a wormhole connects them. Entanglement and wormholes are two descriptions of the same underlying reality. Think about the implication. Wormholes are geometric features of space-time. Entanglement is a quantum informational feature of quantum states. If they are equivalent, then geometry is constructed from quantum information. The space-time connection, the wormhole, is fundamentally just quantum entanglement described in geometric language. The geometry emerges from the entanglement. Space-time never existed as a geometric entity. It has always been quantum information, and geometry is merely a way of talking about entanglement patterns. If space-time is emergent, what does it mean that we experience ourselves as existing in space and persisting through time? We are physical systems composed of matter, which consists of quantum fields, which are excitations of underlying quantum degrees of freedom, patterns in quantum information. Our experience of space-time is how those patterns perceive their own structure. We are embedded within the emergent description, and from our internal perspective, space-time seems unquestionably real. It is akin to a character in a video game experiencing the game world as real. The 3D space in the game is generated by code, by information processing. The character's experience does not make that space fundamental. We experience space-time because we are emergent structures within an emergent description. Our consciousness operates at the emergent level, not the fundamental one. Space-time never existed independently of observers, and observers themselves are emergent patterns in quantum information. Consider causality. In space-time, causality is clear. Events at one location can affect events within their future light cone, but not outside it. Cause and effect are local, limited by the speed of light. But if space-time is emergent, causality might be emergent as well. At the fundamental level in the quantum information description, there is no space-time structure, hence no light cones, and hence no clear notion of causality. Causality emerges alongside space-time. It is a feature of the emergent description, not a fundamental constraint. This does not imply lawlessness. The fundamental quantum evolution is unitary and deterministic in a quantum sense. However, the notion of causal relationships between events in spacetime emerges from this more foundational determinism. Spacetime never existed, and causality as we understand it never existed fundamentally. Both are emergent structures. Recent work in quantum error correction provides further evidence. Deep connections have been found between quantum error correcting codes and the emergence of spacetime in ADS-CFT. In quantum error correction, you encode logical qubits within physical qubits so that errors can be detected and corrected. The encoding has a structure where logical information is protected by being distributed across many physical qubits. It turns out that the emergence of bulk spacetime from boundary quantum information in ADS-CFT has precisely this structure. The bulk is an error-correcting code for boundary information. This means space-time emergence is intimately tied to information protection, to how quantum information organizes itself to be robust against loss. Space-time is not a pre-existing stage. It is an emergent structure that arises when quantum information organizes itself in error-correcting ways. Space-time never existed as a given. It emerges as a method of protecting quantum information. Consider complexity and its connection to space-time. Growing evidence suggests the computational complexity of a quantum state is related to the volume of space-time in certain holographic descriptions. As time passes in the boundary theory, the quantum state becomes more complex, harder to prepare from a simple initial state, and correspondingly, the volume of a specific region in the bulk grows. This implies that time, or at least one notion of time, is linked to increasing complexity. The forward direction of time is the direction of increasing complexity, and space, or at least volume in space, is related to complexity. More complex states correspond to larger volumes. Space-time never existed as a fundamental arena. It is a way of describing the complexity structure of quantum states. This perspective reshapes the future of physics. If space-time is emergent, our goal is not to quantize space-time itself, not to find a quantum theory of space-time geometry. Our goal is to understand the fundamental quantum information theory from which space-time emerges, to understand the degrees of freedom, the entanglement patterns, and the dynamics that give rise to the illusion of smooth geometry. String theory is one approach. Loop quantum gravity is another. The holographic principle and ADS-CFT provide crucial clues, but we lack the complete picture. The theory of everything will not be a theory written in the language of space-time. It will be a theory of quantum information from which space-time emerges as an approximate, coarse-grained description. Space-time never existed fundamentally, and the ultimate theory will reflect this by not assuming space-time as a background. I find this view beautiful. For millennia, humans considered space and time fundamental features of reality, the stage for all events. Newton regarded space as absolute, God's sensorium, existing independently. Einstein revealed that space and time are relative, interwoven, and dynamic, yet still fundamental. Now we are learning they are not fundamental at all. They are emergent, like temperature or pressure, macroscopic properties arising from something deeper, more abstract, and more mathematical. This is a profound shift in worldview. We are not beings existing in space-time. We are patterns of quantum information, and the space-time we experience is a user interface, a way of organizing information that is coherent to creatures like us. Space-time never existed, and this realization is liberating. It means reality is stranger, richer, and more subtle than we imagined. It implies levels of description we have not yet conceived. Scientifically, it is powerful. Recognizing space-time as emergent helps resolve paradoxes like the black hole information problem, guides us toward a theory of quantum gravity, and reveals deep connections between quantum information theory and geometry. Space-time never existed. Acknowledging this stands as one of the great intellectual achievements of modern physics. Let me address objections. You might say, I am sitting in space right now. I am experiencing time passing. How can you claim these don't exist? They exist at the emergent level. Your experience is real as an emergent phenomenon, but emergent does not mean fundamental. Water waves exist. You can see them, measure them, surf on them, but waves are not fundamental. They are patterns of water molecules moving collectively. The wave is real at the macroscopic level, but not fundamental. Space-time is real at the macroscopic level. Your experience of it is genuine, but it is not foundational. It is an emergent pattern of quantum information. Stating space-time never existed does not invalidate your experience. It contextualizes it, showing your experience belongs to an emergent level, not the fundamental reality. Another objection. If space-time is emergent, why does it seem so solid, real, and unavoidable? Because you are an emergent structure. In the emergent description, you are composed of the same emergent space-time you are experiencing. From your embedded perspective, it is completely real. It is like asking why characters in a simulation experience their virtual world as real. Because they are made of the simulation's information. They have no access to the outside perspective. We are embedded in the emergent space-time description. We cannot step outside it in our everyday experience, so it seems absolutely real. But physics allows us to infer the deeper structure, the fundamental level where space-time does not exist. The most radical implication is that space-time is contingent, not necessary. If space-time emerges from quantum information, then different organizations of quantum information might yield different space-times, or no space-time at all. There may be regions of the quantum state or other quantum states entirely where space-time does not emerge, where the degrees of freedom are organized differently and the emergent description is something other than geometry. Our space-time, four-dimensional with its specific geometry, might be just one possibility among countless others. Space-time never existed as a necessary feature of reality. It is a contingent outcome of how quantum information organized itself in our region of the quantum state. Let me bring this all together. Space-time never existed because it is emergent from quantum information. The evidence is overwhelming. The holographic principle, ADS, CFT, ER-EPR, quantum error correction, the connection between entanglement and geometry, its breakdown at the Planck scale. At the fundamental level, there are quantum degrees of freedom entangled in complex patterns. From these patterns, when you coarse-grain and examine collective behavior, space-time emerges as a useful description, but it is not fundamental. It never was fundamental. It is an illusion in the same sense that temperature or waves are illusions, real at the emergent level, but not part of the deep structure of reality. This is one of the most profound insights in the history of physics. We have discovered that the stage on which we believed everything occurred is itself part of the performance, emergent from the actors, arising from quantum information. My entire career has been dedicated to reaching this understanding through the study of black holes, holography, string theory, and quantum information. The more I learn, the more convinced I become. Space-time never existed. That is the truth about the nature of reality that physics has unveiled. It is strange, counterintuitive, and challenges everything we thought we knew about the universe. Yet it is also beautiful, profound, and supported by powerful mathematical and physical arguments. Space-time never existed. Understanding this transforms how we view reality, consciousness, cosmology, and the ultimate nature of existence itself.